Hi, it's Luke. We're going to be looking at some time-independent perturbation theory. We're going to split this up into two parts, I think, as well, or maybe three, depending on how long it takes and stuff. So perturbation theory is applied when a similar problem can be solved from an unsolvable problem. So if you've got an unsolvable problem, we use perturbation theory to almost solve the unsolvable problem by doing something that's similar. For example, the vibrational frequency with the harmonic oscillator gives us a good estimate of vibrational frequencies. So the harmonic oscillator is the red dotted line, and the original actual vibrational frequencies is the blue line, and that obviously gives up like a close enough estimate. So the Hamiltonian is an unsolvable equation, so we can set up to mathematically solve the Hamiltonian by doing this. In perturbation theory, the Hamiltonian can be written as a zeroth order Hamiltonian plus h prime, which is perturbation time independent theory, which means it does not vary with time, and this is the first term in that. So to apply the perturbation theory, we need to know the following. One, we want to be able to solve the zeroth order Hamiltonian, which is this zeroth order. Perturbation is small compared to the zeroth order Hamiltonian. In order to work, if it's large, then it'll be ever increasing or decreasing, I believe. And the zeroth order wave functions are non-degenerate, which means they can't be the same number, and therefore the full Hamiltonian is this. And then we have the lambda for the first one, lambda squared, and these are first order corrections, second order corrections, and so on and so on. And lambda is a constant. The energy of a perturbed system can be given as pretty much exactly the same as the Hamiltonian, just by placing an E there, and the wave function is the same. And the subscript represents the eigenstates, so we're looking at the nth eigenstate, and the superscript is the order of perturbation, so first, second, zeroth, etc. So, as we mentioned, we want to be solving the zeroth order, or the ground state, the ground eigenstate. So, if we sub in the expansion for the perturbation theory, we have all of this, which is just a lot of stuff. And when lambda equals 0, we can get the zeroth order Hamiltonian. And when lambda is to the power 1, we get all the 1 terms. So this is by taking out all of the 0th terms. This is by taking out all of the 1 terms. And this is taking out the 2 terms, and so on and so forth. If you wanted to do the 3 terms, then you're a bit crazy if you ask me, but that's the same. So anything that adds up to 2, essentially, or anything that adds up to 1, so we've got 0th order Hamiltonian, second order wave function, which is, if you can see, what am I looking for? Here, you want to time these two together, that's what it gets you, that's the second order term, which means we can also do this times this, this times this, and so on. So when looking at the first order correction, we don't know this. We know this. We know this. We want to know this. Should I say? We don't know. We know this as well. We don't know this. I think, or we do know this as well. Yeah, we know everything else. So to work out what this is, it's the sum of a linear combination of the zeroth order wave functions, which can also be written like this in bracket notation. So if we sub in for the first order energy correction, we can get the sum of this term here, and that's the wave function essentially, with the bracket, and this as well, which is the zeroth order state. And if we multiply the left by this term here, the zeroth order state, it gives us this, the sum of the linear combination of these terms here. It's not very pretty, so we can say that these two are equal to these two are equal to these two. So that makes it easier to simplify. Oh, so sorry, this is equal to this. Essentially, that's all we need to see. And that means you can put that in instead. This shows normalization, which can be seen here, which is equal to 1, so we can cancel this term. N equals 0, otherwise the integral will be 0. So if we sub this in, n equals 0, c0, all this stuff here, we can cancel these terms. That equals to 1, so that just kind of disappears as well. And then we get E0, and then we can't really change this term up much. We can't really make it any better to look at. C0 is equal to 0, or we're timesing by 0 here, so that's going to be equal to 0, which is fine. And then if we would do a bit of rearranging, we can get this equal to this. Remember, this is the term we want to solve, so if we know that En to the first order correction to any eigenstate is equal to this here, essentially. So you can look at the bracket notation or otherwise. So the first order correction to energy is the expectation value of the 0 order wave function with perturbation, essentially. And we've got an example to put this into play, because I don't know explain things very well, and hopefully the examples explain things a little bit better. So the example is calculate the ground state energy to first order perturbation for a particle in a box with a well of step height epsilon between x and x equals L over 10. So first order correction, we know this term now. The 0th order correction, or the 0th order wave function, is this, which we derived earlier, which was in a previous video, I believe. That's something we need to know. The perturbation is equal to epsilon, that's the step, the well step. And this is between 0 and L equals 10, L over 10. That's where x is. And it's equal to 0 otherwise. So the integral we are given in the end is all of this stuff which we've seen before, plus a factor of epsilon there. We can take epsilon out, or epsilon over 2 out, when we integrate. So we integrate and take a factor of epsilon over 2 out, because we know that 2 sine squared x, because we've got sine squared x here, is equal to 1 minus 2x, and we take the 2 out by dividing it by it, and that gives us this, essentially. So we've got 1 minus cos 2 pi x over L dx is equal to epsilon over L once we've integrated it. Sorry, we've not integrated here. This is just subbing in this. So that gets subbed in. And then we can integrate it, which we've done many times before. If we flick over the page, when x equals 0, the equation is equal to 0. But when x equals L over 10, we get the following. And that equals epsilon over 10 minus epsilon sine pi over 5 times 1 over 2 pi. So for us, for the total energy, we need to do the 0th order perturbation and the which we know already, which is h squared over 8ml squared, plus the first order perturbation theory. And this is for the ground state, the ground eigenstate, because we've got n here equal to 0. We've got some more examples, which I don't know if we'll have time for. Let's see how far we've got. Yeah, we should have time. Okay, so example 2, we've got a particle of mass m, which is subject to a potential. So the potential here is V equals a half m omega squared x squared plus gamma x to the power 4. So we've got a harmonic oscillator term and an anharmonic oscillator term. Gamma is less than 0 when we've got a negative anharmonic, and that's the potential. Find E01 is what we want to find. So this is the information we've been given essentially. And we've been given this as well. This is in the question. So we know what the perturbation is. This is the anharmonic effect when we're not using the harmonic oscillator. So we can say that the integral is therefore this term multiplied by this, and then we've got x to the 4, e to the, which is from there, e to the minus mw over h bar x squared, which is essentially this term here. The 2 disappears due to the wave function being squared, which is nice. And then we also get given this in the question. So by being given this, we can show that if we make A equal to m omega h, that we can essentially get this equation. So if we sub it all in, we can cancel these terms, and we can get gamma just here. We can get that. So when gamma is less than 0, the energy is lowered, and when gamma is more than 0, the energy is increased. So then rattling through these things, hopefully the pages are more helpful than my explanations, because I don't really know what I'm talking about, I'm not going to lie. Example 3. Calculate first order correction to the energy of a particle confined in a box and evaluate it for A equals L over 10 when n equals 1 or 2. So that means En where the n is equal to 1 or 2. And this is the equation we've got here. This is the problem we've got here. So we know that the perturbation is epsilon again. In between half L minus A, which is the length of the perturbation this time, and plus. So it's essentially just stating this part. Or 0 otherwise, as in the last example 2. And as you can see here, we know this from before. If we sub in the perturbation in the wave function, we can get this. Use this correlation again to say that 2 sine squared x equals 1 minus cos 2x, and we can take out the factor of 2, which removes this from the outside there. Once we integrate it, we get this, which we've done many times before, and then we can sub in our limits, which is all of this mess. And once we clean it up a little bit, we get this. When A is equal to L over 10, we can get all of this, and this is the examples. Then the perturbation is much smaller for n equals 2, as you can see. And this is good because this shows the system is calming down. It's just better that the perturbation is lowering each time. And with that, that'll be the end of this. Next time we're going to be looking at like first order perturbation theory and other stuff like that.